4.4 we learned about combinations, permutations, counting principles. Okay. In 4.5 we're going to take that information and combine it together with probability that we did earlier in chapter 4. So we're going to use those strategies and we're going to put it together to find some probabilities of some things. Okay. One of the issues that you're going to have in this section is all the different kind of categories or slots that each kind of problem is put into. And it's going to require you to kind of think hard and long about what the problem is asking and what you're looking for. And then once you figure that out, you got to decide, is it a permutation, is it a combination, and kind of go from there. So that's what's going on in 4.5. First, we're going to use the same counting rules to find probabilities that we just did. That's like what I just said. And we're just going to divide the number of possibilities of what we are looking for, what we did in 4.4, by the total number of possibilities. So the same general framework that we use to find any probability of something, probability of the event occurring divided by the total number of possibilities, that concept is not going to change. How we determine what the probability of the event is, or the number of ways that that event can happen, divided by the total number of possibilities. Now we're going to use some of those counting principles and combinations and permutations to do that. Here's the first problem. We're gonna use cards a lot in these problems. Okay, we're gonna find the probability of getting 4 aces. So 4 of a kind, right? That's a pretty good poker hand from an ordinary deck of cards. Besides a royal flush, that's the best hand you could get. Okay, 4 aces.
Unless you get a Yahtzee.
That's not cards. That's dice. All right. Now, got to keep in mind, what you have to understand in this problem, we have 2 different categories. We have the category of getting 4 aces. That's one category. Then we have 5 cards being drawn. So there's a whole another situation with 1 card. So I got 4 cards as one situation. I have 1 card as another situation, assuming the first event already happened. Now, what's different about this problem from what we did in 4.4, it would have just said, how many ways can you get? In this case, we want to know what the probability of all of that is. Right? So that's where it changes a little bit. So first of all, we've got our 4 aces. Okay, so we need to figure out how many ways can you get 4 aces out of a deck. Does the order matter? Is there a difference between the ace of diamonds, if I said ace of diamonds, ace of hearts, ace of clubs, ace of spades? Is that different than ace of clubs, ace of hearts? There's still 4 aces, right? The order doesn't matter. So we're talking about what? Combination or permutation? Combination. We're talking about combination. How many aces are in a deck?
4.
How many am I going to choose?
4.
So I'm going to get 4 aces. So there's 4 aces and I'm going to choose 4 of them. So the first part is going to be a combination of 4 things because there are only 4 aces, and then we're going to choose all 4 aces. Okay? That's the first part. Now, that's just the first 4 cards, or 4 of the cards. I need a 5th card. Okay, because we're going to draw 5 cards. Understanding the aces are gone. I can't draw an ace again. We drew all the aces. So how many cards are left to draw from?
Probably 0.
There's 48. Now, I'm going to show you 2 things here. First of all, there's 48 cards as possibilities for the 5th card.
No.
In order to use combinations, okay, what it would look like is this. Combination of 48 things to choose from, and I'm choosing 1 of them. So the combination formula will give me 48. Now that's just the probability of the event occurring. That's just the numerator. How am I going to find the total possibilities for drawing cards at all? So this is just the numerator. So there's the fraction bar. On the bottom I have to have all the total possibilities of 5 card hands.
Who cares?
Okay, is it a combination or permutation?
Combination.
It's still a combination. So the order doesn't matter. I have 52 cards. How many am I choosing?
4.
5. Okay, so the total number of possibilities for getting a 5-card hand out of an ordinary deck of cards is 52. Choose 5. So now that's our probability. Okay, so again, the top was like what we did in 4-4. Tell me how many there are. Now we're going to divide by the total possibilities, and that will tell me the probability of getting 4 aces in a 5-card hand. Okay, so go ahead and figure that out. Find the answer. The top should be 48. Okay, there's one way to do this. So you get 4 factorial over 4 factorial times 0 factorial. So this is just 1. So the top is just 48. This, when you figure it out, you should have gotten 2,598,960. Okay? So at this point you have the option then of converting this to a decimal or reducing the fraction. And I went ahead and reduced the fraction. And so there's 1 out of 54,145 ways to get the probability is 1 out of 54,145 to get a hand with 4 aces.
Are all the examples like the same?
They're a little bit different, so you get a different flavor of what you're supposed to be doing in your homework. Next one, like this one. This one has actually 4 parts.
Oh, jeez.
And you're going to see problems like this in your homework, and it's going to be really important to understand what you're supposed to be doing in each scenario. Because in each scenario it's a little bit different. And being able to complete some of the questions are dependent on what happens in some of the previous questions. So we'll talk through all of these situations. One of the things that's really important when you're working in these types of problems is to determine what you're actually being asked to find. And that's going to require some reading and rereading and really trying to think about what they're asking before you can proceed to just throwing numbers to the paper. Okay? You've really got to decide what's going on in the problem. So there's this box that has 24 transistors in it overall. 4 are defective. Okay? And this is not atypical of having a box of a lot of things where some of them aren't quite perfect. Okay? So 4 transistors from that box are going to be sold at random. So there's a chance that some of those 4 transistors that are sold are defective. It may be that you happen to sell the 4 that are all defective and a person buys 4 defective transistors. It may be that none of them are defective. Okay? And it may be that some of them are defective. Okay? And so what we're going to do is determine all the different probabilities. Now, in A, if it says, so you sold 4 are being sold, exactly 2 are defective. What is A actually telling us? Half of the ones we sell are defective. So if that means there are 2 defective, what does it say about the other 2? They're not. They're fine. Okay? So in part A, the person gets sold 2 defective ones and 2 not defective ones. Okay? So what we're looking at is this situation. And we need to find the probability of the 2 defectives, and then we're going to multiply that by the probability of the 2 that are not defective. Let me say that again because I didn't quite say it right. We're gonna find the probability of taking 4 out of the box where 2 are defective and 2 are not. Okay? And what we're going to multiply are the number of ways to get 2 defective times the number of ways to get 2 not defective divided by the total number of ways to get 4 transistors out of there. Okay? So first of all, in the 2 defective category, how many are there to choose from?
24.
Okay? 2 defective. How many defective ones are there to choose from? Okay, there's 4 that are defective, and I'm going to choose 2 of them. So in this category, it's a combination of 4 things, choose 2. Because we've already established we're choosing from the defective group. Okay? Now, For the two that are not defective, how many are we choosing from? 20. Because of the 24, there's only 20 that are good. And I'm choosing 2. So that's going to be a combination of 20, choose 2. Now, I have to multiply those together and divide by the total number of ways there are to pull 4 transistors out of the box. So what's the total possibilities? What's going to be on the bottom here?
24C4.
24C4. Okay? Figure that out. Put your answers in decimal form. Put your answers in decimal form. Yeah. Go 3 places with your decimal. 3 places.
How do you put that?
You have to be able to, you have to know the formulas for combinations and you have to write that out. Okay? Make sure that you're writing that information out because when we get to that test, you're going to have to know the formulas. So make sure you write that out. Okay, so combination of 4 things, choose 2 is what? What is this? 6. What's this one? 190. What's this?
10,626.
Correct. Okay, so that's really what we're doing here. And if you still don't know the formula for combination to come up with these numbers, that's something you need to work on to get there. Okay. Now, as it turns out, 6 goes into 10,626. Okay, so I can reduce it down there and get 0.107. How many had that? Raise your hand if you had that. Okay, so it's like 10% of the time you're going to get exactly 2 defective, which is pretty low. Which is why businesses continue to put defective items in boxes to sell you. Because the chances of you getting 2 bad ones is pretty low. Alright? Now, part B. None is defective. What changes with this problem for part B?
It's 4C0, right? No, it's 20C4, right?
Right, so essentially we eliminate this category. And we only choose from this category. So what that's going to look like is this. We're not allowed to choose any of these 4. Okay?
Interesting.
None is defective, which means all of them are not defective. Okay? And again, my total number of possibilities is the same. I'm still choosing 4 from the 24.
Wouldn't you just use the same numbers from A? Just not include the 4C2?
Well, but we're choosing 4 of the 20, not 2.
Um,
We're choosing 4 of the 20, not 2, so that changes things a little bit. Okay, so take a look at that. So here's what your top number should be now. Bottom number's still the same. So the total number of possibilities for the bottom is going to be the same for all of these problems. All right. So to get 4 that are not defective, the probability of getting 4 that are not defective is 0.456 or about 46%. So think about that for a sec, right? There's still a pretty good chance you're going to get a defective one, right? The chances are better than 50-50 that you're going to get a defective one in that group of 4. And they're still going to sell them to you. Okay? Now, what changes for part C if all are defective?
It's 4C4, get rid of the other side.
So right, so this number now is gone. There are none in the group that you select that are good. All of them are defective. So this changes to only choosing from the 4 that are defective, and we're going to choose 4 of them. So what we should have for that is where you're choosing 4, choose 4, which there's how many ways to do that? 1. Okay? So this is really just 1 over 10,626, which is pretty small. The likelihood of you getting all 4 defective transistors out of the 4 that you buy is pretty small. Okay? And next we need to talk about D, because D is a little tricky. Next one, this next one here is where we've really got to think about what it's asking, okay? At least one defective. That means you could have 3 that are good and 1 that's defective. You could have 2 and 2. You could have 1 that's good and 3 that are defective, or you could have all 4 defective. So you have options here. You could actually find all of those probabilities of those, what did I give you, just 3 or 4 scenarios right there, and add them all up. But that's a lot of work, okay?
Way too much work.
In a situation where at least 1 is defective, what is the one situation that is not included in that group?
When all of them are.
Oh my gosh.
Okay, when none are defective. Okay, and in part B, which is why it's still on the screen, we found out what the probability is that none are defective. That's the one group that's eliminated from part D. So how could I use that information to come up with part D?
1 minus.
1 minus. Okay, remember complementary events. So 1 minus the situation where there is none defective, which we already found. Okay? Alright, and in that case with the fraction, I don't know why I bothered to do that. I should have just subtracted the decimal, but I didn't, because I was doing fractions all the way along. Okay? So, when you see that at least, or at most, what you really want to think about is, think about it as a complementary event, and see if you haven't already figured out what you have to subtract from 1. In all likelihood, that will happen. Okay? Any questions about anything? That was it. I'm done with it.
Done?
Done.